Hey folks, Miss Gosling here. In this series of videos, you are going to learn about everything that led up to our modern understanding of quantum mechanics. So in this video, we're going to start out with Einstein and de Broglie. I know this looks like his name looks like it's pronounced de Broglie. It's French. It's de Broglie. By the end of the video, you are going to be able to describe the wave-particle duality of both light and matter. So let's go ahead and get started, shall we? And let's start by introducing our cast. So on the left here, we have Mr. Albert Einstein, famous, of course, for general relativity, but also a fundamental player in building our understanding of quantum mechanics. And on the right, we have Mr. Louis de Broglie, who you may have learned about in your chemistry class, and whose description of the waves, whose description of matter waves is fundamental to the development of the Bohr model of the atom. So with that, let's go ahead and get started talking about what their contributions were and how we now have a better understanding of what happens to matter and to light on a very, very fundamental level. And we're going to start by discussing the photoelectric effect. Now, according to the photoelectric effect comes from a very straightforward experiment where we start by shining light on a metal surface, and we can see here where that is happening. Now, that metal surface is within a vacuum chamber, and is set up so that the electrons that come off of the metal surface hit a detector of some kind. Those electrons, of course, are going to move and are going to generate a current. So when we look at the photoelectric effect from a classical physics perspective, what we expect is the longer the light shines on the metal surface, the more energy collects on that metal surface, and therefore the more electrons are released, and the stronger the current we measure. So again, more light. So that can be done by increasing time or intensity. And per classical physics, we expect that that will cause energy to collect on the surface, and then electrons are released, causing a current. So what this suggests is the longer I shine a light on a metal surface, or the higher the intensity of the light that I shine on the metal surface, the more electrons will be released, and the current in my circuit is going to continuously increase. However, when we actually do this experiment, that's not what we find. Instead, what we find is that let me erase our classical physics perspective because it's not correct. But what we find when we actually do this experiment is that the frequency of the light is what affects whether or not the electrons are released from that metal surface. So higher frequency results in greater number of electrons being released, results in a greater current. So what the photoelectric effect says is if you want to increase the current or the amount of electrons released from a metal surface, thus the current generated by shining light on a metal surface, then you're going to want to increase the average frequency of your light. So if we're shining monochromatic light, blue or purple or ultraviolet radiation is going to release more electrons than infrared or red or yellow light, because those former ultraviolet light is much higher frequency than infrared light. Now we call the minimum frequency so we define the threshold frequency here, which is represented by F naught, and we're going to define that as the minimum frequency at which an electron is released. And that is going to be different for different kinds of metal. So what happens if I shine light that's higher than that frequency, that's higher that frequency than F naught? Well, those photons that are released are going to have a larger kinetic energy. So that energy of that photon is going to go into that electron. And if my frequency is below that threshold frequency, then no electrons will be emitted at all. So again, what this says is that the energy of the photons in the light has to be high enough to release the electrons from that metal surface. And from the photoelectric effect, we get this equation on the bottom left, where the maximum energy of the electron is equal to h, Planck's constant, times the frequency of the photon, so the frequency of my light, minus the work function, which we define as the work required to overcome the attractive forces that act on the electron within the metal. So the force is holding that electron to the metal. So if the energy of the photon minus so what we're saying is that the energy of the electron is equal to the energy of the photon minus the energy required to detach that electron from the metal. So we can also say then, using to find our threshold frequency, E max, the energy of that electron, is going to be 0. And that will be equal to h times F naught minus phi. So again, it's going to, when we are to find our threshold frequency, we'll simply set the energy of that electron to 0, since that is the minimum energy required to pull it away from the metal. So why did I get into all of this? Well, what the photoelectric effect suggests is that light acts as both a particle and a wave. So we know this because it is a single electron that frees the photon. And we know that because if it were about the energy pooling up from the light on the metal surface, then that initial classical model would be correct. So the longer that we shone light on the metal surface, the greater the current would become. However, because the current is dependent on the frequency of the light rather than the intensity of the light, or the energy that built up on that metal surface, that suggests that a single photon is used to detach a single electron, thus suggesting that light can be broken down into photons, into small parts. It can be quantized into pieces versus being a continuous spectrum. Okay, so we know that light behaves as both a wave and a particle. What about matter? So, as I mentioned earlier, our second main cast member for this video is Louis de Broglie, who suggested that since waves can have particle-like qualities, so light can have particle-like qualities, therefore it makes sense that the opposite would be true as well. So matter should have wave-like qualities as well as its traditional particle-like qualities. Now, de Broglie provided the theoretical backing for matter waves, for suggesting that electrons can act like waves in the same way that photons do. But this being physics, his ideas, of course, could not be accepted until we had experimented to see if we had any experimental data suggesting that theoretical backing. So in 1925, two American physicists experimented looking at electron diffraction through a nickel crystal. So they were looking at how electrons diffract through a crystal. And from that experiment, they were actually able to see that you get a similar electron pattern, a similar diffraction pattern for electrons as you would if you had set photons through that crystal. So because we can get a diffraction pattern for electrons, that suggests that electrons, therefore, have wave-like properties. So just like how light can act as a particle, matter electrons, particles, can act as waves. So let's talk takeaways. I'm going to pause the video here before we get into the implications of all of this. And let's talk our takeaways. So first of all, the photoelectric effect suggests that light can behave as a particle, and de Broglie and electron diffraction together demonstrated that matter can behave as both a particle and a wave as well. So both light and electrons behave as both particles and waves. So with that, it is now time for you to learn a little bit more about the implications of matter waves. Best of luck and enjoy the next video.